The first images from the James Webb Space Telescope were supposed to show us a quiet, newborn universe. Instead, they showed galaxies that already looked grown, bright, massive, organized, all appearing when the universe was only a few 100 million years old, before there should have been enough time to build anything like that. Unless something fundamental is missing from the story. Unless the first objects that lit up the cosmos weren't powered by fusion at all. Unless the first stars ran on invisible fuel. And that brings us to an idea so radical it could realign the entire early universe timeline.
You clicked for dark stars. Good call. Those early, massive galaxies in JWST's first snapshots? They shouldn't exist that soon after the Big Bang, unless the first stars weren't stars at all. In this video, we'll explore the radical idea of dark stars, objects powered not by fusion, but by dark matter heating. Stay with me to see how that single switch flips the timeline of the early universe, explains rapid growth into supermassive black holes, and resolves today's biggest cosmology headache without breaking the laws of physics. JWST didn't just turn up faint smudges at the edge of time. It saw compact, bright systems that looked like grown galaxies while the universe was still learning to walk. How does anything assemble that fast when the cosmic clock reads a few 100 million years? Set the scene. We're between about 300 and 500 million years after the Big Bang, an era when the fog of neutral hydrogen starts thinning and reionization gets going. In the standard picture, dark matter halos gather first, gas trickles in, cools slowly, and forms the first small, metal-poor stars. You expect dim knots, not city lights. Feedback from newborn stars and early supernovae should heat and stir the gas, limiting rapid growth. Under lambda CDM with conservative star formation rules, the early sky should be a whisper, not a shout. Here's the rub. Several JWST candidates at redshifts around Z10 to 14 appear too luminous and too hefty. Photometric fits point to stellar masses that can reach into the billions of suns and sizes that suggest organized systems, not chaotic clumps. If those numbers hold, the usual recipes, how gas cools, how stars form, how feedback throttles them, struggle to keep up. Even using optimistic efficiencies, the timeline feels tight. Walk through the expected path. First, population 3 stars ignite in small halos, providing the first UV light and the first metals. Halos merge, but mergers scatter gas and spark feedback that slows the next round of star birth. Cooling follows rules. Atomic lines matter, molecular hydrogen can be fragile, and metals are scarce at the start. Every step is a bottleneck. Supernova winds and radiation pressure should push back on the very gas you need for growth. By these checks, you'd build slowly, brick by brick. Now the data points. Objects labeled at Z12 to 13 carry rest frame optical light in the JWST bands, giving hints of Balmer breaks that suggest an underlying grown-up stellar population or at least a complex star formation history. Some fits yield specific star formation rates that are high enough to strain standard duty cycles. Are these exact numbers locked in? Not yet. Photometric redshifts can shift when strong emission lines mimic continuum shapes, and selection effects favor the brightest sources. Gravitational lensing can also boost apparent brightness. But even after you factor in uncertainties and the chance of interlopers, the upper end of the distribution keeps nudging the limits. Think of early galaxy building like putting up a skyscraper overnight with no cranes, no steel deliveries, and a city curfew. The supply chain of baryons is slow. Cooling, fragmentation, and feedback are your red tape. You can cut a few corners, but you don't get to the penthouse by dawn under the usual code. Spectrally, several candidates show rest frame optical features that hint at evolved stars and intense recent bursts at the same time, a tricky mix. High equivalent widths in some lines, if present, can inflate mass estimates or masquerade as older populations, so the interpretation is delicate. Yet the broad trend remains: bright, compact, and busy very early. So what gives? Maybe we misread some photometry. Maybe our physics for early cooling, turbulence, or star formation efficiency is missing a knob. Or maybe a hidden energy source did part of the heavy lifting before classic fusion-dominated star clusters took over. That last path opens a different growth curve, one where energy keeps gas puffy and accretion-friendly while still lighting up the sky. Here's the mini twist. The early universe could host objects that look star-like or even galaxy-like in broad strokes, but shine for reasons other than fusion. If such objects built mass quietly while staying luminous, they could front-load the system before the usual rules kick in. Hold that thought, because the next step is to look at a proposal that slots neatly into the timeline. Dark stars as a missing rung in the ladder, pre-building light and mass so that by the time fusion dominates, the universe already has a head start. What if the first stars were bloated giants running on invisible fuel? Not a spark of hydrogen fusion yet. Heat from dark matter annihilation doing the lighting. Here's the idea. In the earliest dense halos, gas and dark matter share the same gravitational well. As gas sinks toward the center, the dark matter distribution tightens too. In that compact core, the dark matter particle. Here's the idea. In the earliest dense halos, gas and dark matter share the same gravitational well. As gas sinks toward the center, the dark matter distribution tightens too. In that compact core, the dark matter particles collide and annihilate with their own kind, and the released energy heats the gas. You end up with an object that looks star-like because it's luminous, but the engine is different. Instead of a blazing fusion core, the power source sits in the central dark matter cusp, soaking the surrounding gas with a steady energy drip. That flips the usual playbook. A normal protostar contracts, heats up, and eventually reaches temperatures that ignite fusion, blasting out radiation and winds that push back on infalling gas. A dark star can stay cool at the surface while shining from within. The interior heat halts rapid collapse before the core gets hot enough to fuse. With a cooler photosphere, the radiation pressure is gentler, so the object swells to a huge radius and keeps feeding calmly instead of blowing its food away. The mechanism hinges on adiabatic contraction. As baryons fall inward, they deepen the potential well and drag dark matter orbits tighter. If the dark matter is made of weakly interacting massive particles, their rare interactions become frequent enough in the cramped core to annihilate in pairs. Each annihilation releases standard model particles and photons, which thermalize and provide pressure support. That heat source counteracts gravity just as fusion would in a later star, but without the extreme core temperatures. The result is a stable, puffy configuration that can persist as long as the annihilation rate supplies enough power. Now feed it. Because the surface stays relatively cool, ionizing radiation is reduced, so surrounding gas doesn't get blasted into outflows. Accretion stays efficient. Instead of stalling at dozens or hundreds of solar masses, growth can continue across orders of magnitude. Models outline paths to 10 to the power of 4, 10 to the power of 5, even 10 to the power of 7 solar masses when the fuel keeps coming, much faster than you'd expect if fusion-driven feedback were in charge from the start. The geometry helps too. A big radius increases the cross-section for capturing material, and the gentle luminosity keeps the inflow stable. How would you spot one? Look to the infrared. A dark star's large radius and low surface temperature shift the light into redder wavelengths, especially after cosmic redshift. You'd see a bright, smooth continuum without the strong ionization signatures that hot, compact fusion stars produce. Spectra would look cooler, with weaker high-energy lines and a lack of hard UV-driven features you'd expect from a young, metal-poor stellar population. The effective temperature would sit in the few thousand Kelvin range while the luminosity rivals or exceeds that of entire small galaxies, thanks to the vast emitting surface. Modeling suggests lifetimes long enough to grow and shine through a chunk of the early epoch, then fade when annihilation power drops or collapse when the central support fails. A few candidates in deep fields have been flagged for these traits: oversized inferred radii, red continua, and brightness that seems high for their supposed age. Each case needs careful checks because emission lines and lensing can mimic some signals, but the profile stands out. If such giants exist, their finale has big consequences. When the dark matter heating wanes, the swollen star can contract, ignite fusion briefly, or tip straight into collapse, leaving behind a massive black hole. That kind of seed shortens the road to the supermassive black hole seen early on. Swap the ignition source, and you get quick mass assembly, softer feedback, and black hole seeds preloaded for rapid growth. Confirming even one would link the bright early galaxies and the fast-rising quasars to a single process, turning a headache into a testable path forward. And that sets the stage for how targeted spectra and lensing will decide whether dark stars are rare curiosities or a foundational phase of the first light. Start the universe with dark matter-heated stars, and those early bright galaxies stop looking like rule breakers. Rapid black hole growth no longer needs special tricks. It follows from oversized, cool, luminous seeds that form fast and feed efficiently. That shifts the crisis into a testable scenario instead of a contradiction. Watch the next JWST spectra and lensing-aided targets. If we catch a cool, bloated source with luminosity too high for fusion and spectra lacking hard UV, the early timeline gets a clean rewrite. One unseen fuel source could explain that impossible light. The next dataset might decide whether dark stars stay theory or become the headline.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.